So far, most of our attention has been paid to developing techniques for finding antiderivatives. So we have now developed W substitution, integration by parts, integration by partial fractions. So we have a fairly large collection of integrals that we can do now using the fundamental theorem of calculus. Today we start looking at applications of integration, so we'll start to see the payoff for all of the work we've done in developing our techniques, because we're going to see how integration can be useful to solve a variety of real-world sorts of problems. The applications we're going to take a look at all involve the same method for setting up our problems. They all rely on viewing each situation as an integral, and then using our fundamental theorem of calculus and the techniques we've already developed to evaluate the integral. But to set up the problems, we actually need to understand the definition of the Riemann integral, which we've seen before, but we're going to take a few minutes to review that definition. We start with some continuous function on the interval a to b, and our goal is to find the area underneath that function. The way we normally start is we partition the interval into lots of little subintervals. So I'm just going to do a quick sketch here where we've got our continuous function f of x over some interval a to b, and we're interested in knowing the area under that curve. Our first step is to partition the interval, or split it up, into lots of smaller intervals that we call subintervals. So here I would have my x1, my x2, x3, and so on, down to n minus 1, and finally the right-hand endpoint is always my last x sub n. Note that the width of each subinterval is given by the right-hand endpoint, which in general is this xi, minus the left-hand endpoint, xi minus 1. And if we've divided our interval a to b into equal subintervals, then each of those has length b minus a, which would be the length of the whole interval here, divided by n, the number of subintervals that we've chosen. From each subinterval, we select some point c sub I, and a common selection is just to select the right-hand endpoint. So for the first interval, my first endpoint would be x1, my second interval I would take x2, and so on. And now we form rectangles over each of the subintervals, where we determine the height of each rectangle by evaluating f, in this case at the right-hand endpoint. So this particular height, for example, would be f of x3. With f of xi as the height of each rectangle and delta xi as the width of each rectangle, the product of height times width gives us the area for each rectangle. And if we sum the areas of all the rectangles, then what we get is a decent approximation for the true area under the curve. So on the left, we have the true area under the curve from a to b. And on the right, we have the sum of the areas of all of our rectangles. Now we typically see that the more rectangles we use, the better our approximation to the true area will be. So that motivates us to not just take a lot of rectangles, but in fact take a limit, as the number of rectangles increases without bound. In other words, we take the limit as n goes to infinity, and that defines the Riemann integral. This is an applet we've seen before that allows us to visualize the definition of the Riemann integral more easily than trying to sketch our own pictures by hand. As it's set up here, the function we're integrating is 0.5 x squared plus 1, and our limits of integration are 0 to 3. We have started off the applet with having chosen 2 rectangles to make our approximation to the true area. And we can see by looking at the calculated upper sum, which is the area of the taller rectangles, and the calculated lower sum, which would be the area of the pink or red rectangles, that using 2 rectangles to approximate the area is not going to do a very good job. But it's easy to increase the number of rectangles. I can click on the black dot here and slide to the right. And if I stop at 8, we see that now each of our rectangles has a much smaller error when compared to the area under the curve. Our upper sum is now much closer, 8.3789, to the true area, which is 7.5, and the lower sum is closer than it was before as well. So the idea behind our definition of the Riemann integral is we should be able to do better by taking more rectangles. Here I've stopped at 40 rectangles, and we can see visually that we're doing a much better job now than we did before. And the applet also calculates the area of the taller rectangles. It's about 7.67, awfully close to the 7.5. And the area, if we added up all of the red rectangles or lower rectangles, gives us about 7.3. Now the best this applet can do is 100 rectangles, and we see there that we are getting even closer to the area under the curve, which is 7.5. We're about 7/100ths too big for the upper sum, and same goes for the lower sum, but we're below the true value there. So I would encourage you to open this in PowerPoint. You can also get to it through the website GeoGebra. We'll talk more about that in class as well, but these sorts of apps are fun to play with and can help sharpen our intuition about what's going on. Once we have set up an application problem using the definition of the Riemann integral, eventually we'll need to evaluate those integrals to completely solve the problem. Evaluating using a definition is awfully hard and usually really messy, and in some cases it'll just be intractable. Instead, we enjoy using the fundamental theorem of calculus when possible, because that boils the entire area finding process down to a simple calculation if we know an antiderivative for little f. We have now expanded the collection of functions that we can find antiderivatives for, because we now know the methods of substitution, integration by parts, and partial fractions. Occasionally, those methods will not be enough for us, or the integral will just be too messy, and we'll rely on some sort of computer software like Wolfram Alpha or a handheld calculator to actually get a value for the integral. Coming up in the series of examples, we're going to start seeing how to solve problems by setting them up as a Riemann integral, but then evaluating them using the fundamental theorem of calculus, or occasionally a computer. Here we outline the basic method that we'll apply not only to the problems we do today, but those that we'll be doing in the coming weeks as well. Our first step will be to split the problem into pieces we know that will approximate the situation. This is what we just did when looking at the definition of the Riemann integral for area under a curve. Curved areas are hard, but we know how to find areas of rectangles. So we split our area problem up into approximating rectangles. Once we did that, we had to figure out the area of each rectangle. In general, we'll be figuring out the contribution to whatever the application is for each little piece that we have split our problem into. Once we know how to find the contribution of each piece, like the area of each rectangle, we approximate our solution by adding up the contributions of all the pieces, just like we added up all the areas of the rectangles. Once we've done that, we know we can get an exact solution by taking a limit as the number of pieces goes to infinity, just like we took the Riemann integral to be the limit as the number of rectangles goes to infinity. Finally, we recognize that what we've done is in fact the Riemann integral, which allows us to then evaluate it using the fundamental theorem of calculus, one of the methods that we've been studying, or in some cases we'll turn it over to a computer to find the value for us. There are a few facts from geometry that'll come up fairly often, so I wanted to remind us of some of those facts. First up, the Pythagorean theorem. We have a right triangle here, and if that's the case, then a squared plus b squared will be equal to c squared. Now, what about similar triangles? Well, here I'm going to let the height be capital B, the width capital A, and the hypotenuse for the large rectangle capital C. Inscribed in the larger triangle is a similar, smaller triangle. I'll call the sides for the smaller triangle little a, little b, and little c. Similar triangles tells us that the ratios of the corresponding sides are always the same. So little a over capital A is the same as little b over capital B, and little c over capital C. Lastly, I wanted to take a look at the volume of a disk, or you can think of this as a really short cylinder. So we'll call this the radius, little r, and the thickness, just because we'll be using this notation a lot later, I'm going to call that delta H for the thickness, or if you like, the height. We get that the volume of the cylinder is the area of the circle, pi r squared, times the thickness, or the height, delta H. Our first few examples involve using integrals to find volumes of shapes that we already know. This first example asks us to find the volume of a cylinder of radius 3 and height 10. We know from previous work that the volume of a cylinder is pi r squared h, where r is the radius and h is the height. So for this particular cylinder, that's pi times 3 squared times 10, which we can write as 90 times pi. All right, so we already know what the volume is supposed to be. The nice thing about that is when we apply an unfamiliar method to a familiar volume, we can check to make sure that the method is making sense. We need to slice the figure into pieces that we know. So those pieces at least approximate the volume we're after. If we slice parallel to the base of the cylinder, then each slice would look like a thin circular disc. We let h be the distance from the slice down to the base of the cylinder. Since this represents a typical slice, we'll call the height h sub I, the height of the ith slice, and we'll call the radius r sub I, for the radius of the ith slice. Now the thickness will be the change in the h, or delta hi. Next up, we need to figure out the contribution of each piece. In other words, we need to find the volume of one of our slices. Well, we know the volume of a disk is pi times the radius squared times the thickness of the disk. Because our cylinder has radius 3, and that radius doesn't change, the radius of each of the disks is also 3. So this becomes pi times 3 squared delta hi, because r sub I is equal to 3, no matter which disk we are thinking of. So the volume of the ith slice or ith disk is 9 pi delta hi. Next up, we add up the contributions of all of the slices to get an approximation to the total volume. That would be the sum from 1 to n of the volume of the disks. So I would get 9 pi delta hi. Well, if we think of that as the approximate total volume, then taking more disks would give an exact volume. And from there, we have to recognize that what we've just done is define a Riemann integral where the function is just the constant 9 pi and the delta hi, as it gets thinner and thinner, becomes our dh. And now we need to think about the limits on the integral. So we need to think about what's the smallest value h can take. H could be all the way at the bottom of the figure. So we can go from h equals 0 up to the very top of the figure. But remember, the height of the figure is 10. So the largest possible value for h would be 10. We've set up our integral, and now we use the fundamental theorem of calculus to evaluate it. The integral 0 to 10 of 9 pi dh would be 9 pi times h, evaluated between 0 and 10. That would give me 90 pi minus 0, or 90 pi. And note, this is the same volume we determined by using the formula for the volume of the cylinder at the outset. Before moving on to the next example, I did want to note that I've been a little bit careless in the language that I've used in the setup of the problem in one place in particular. That is, in number 2 here, I said that the total volume would be approximately the sum of the disks. And I said that because that is how the problems will usually work. When we do our slicing and add up the slices, we get an approximation to the true answer. Because we started with a cylinder and all of the disks are, in fact, just thin pieces of the cylinder, this total volume here would actually be an equality and not an approximation. The method, though, is what I want to focus on, and to be consistent, we used an approximation there instead of the equal sign. Next up, we have the task of using an integral to find the volume of a cone of radius 3 and height 10. As was the case with the cylinder, the volume of a cone we already know to be 1/3 pi r squared h, where r is the radius and h is the height. So we get 1/3 pi times 3 squared times 10. And if we simplify that, we get 30 pi. And that gives us something to shoot for as we're applying this new method of finding volumes. I want to start by marking the dimensions of our cone. So here's the radius. We're told that's 3. And then the height is the perpendicular height from the top down. And we're told that that is 10. Next, we have to think about how to slice the figure so that we end up with shapes that we know how to deal with. Like we did for the cylinder, we take our slices to be parallel to the base of the cone so that what we end up with are thin circular discs. I'm going to let h be the distance from the vertex of the cone up to a disk. That's my h sub I for the ith slice. And I let the radius of this slice be r sub I. And the thickness of the slice is delta h sub I. Now, disks are figures that we know how to find volumes for. So when we go to start setting up the problem, I want to find the volume of a disk or slice, and that's going to be pi times the radius of the slice squared times the thickness of the slice, delta hi. Now here's where the problem's a little harder than the one before. We need all of this to be in terms of just one variable. And since the delta h becomes my dh in the interval, that's telling me that the variable of integration has to be the h. So I need to rewrite r sub I in terms of h sub I. Here's where our similar triangles come in handy. If we do a side view of the cone, where I know the top has radius 3, this perpendicular distance is my height, 10, then this section would represent the radius of one of my slices, and the inside height would be the height of one of my slices. Because of similar triangles, I know that r sub I over 3 is the same as h sub I over the total height of 10. So my r sub I is 3hi over 10. That allows me to now write the volume of a disk purely in terms of h sub I. So I get pi 3hi over 10 squared delta hi. And I can rewrite that if I want to simplify it maybe a little bit. And I would get pi times 9hi squared over 100 times delta hi. So that's the volume of the ith disk, one of many imagined slices for the cone. Once I know the volume of one of my slices, I can approximate the total volume of the cone by adding up all n of the slices. And if the total volume is roughly equal to the sum of n slices, then I would have a better approximation with more slices, and in fact an exact value if I take the limit as the number of slices goes to infinity. From here, we have to recognize that what we've just done is set up a Riemann integral so that my total volume we can think of as an integral of the function that's inside the sum. So that's 9 pi over 100 h squared. And then the delta hi becomes the dh. You can think of that as an infinitely thin disk. And the limits of integration are the smallest possible value for h. It could be all the way down at the vertex, so 0 for the lower limit. And it might stretch all the way up to the top of the cone, which would give us an upper limit of 10. Now that we've set this up, we use the fundamental theorem to actually evaluate the integral. The antiderivative for 9 pi over 100 h squared would be 9 pi over 100 times h cubed over 3, evaluated between 0 and 10. I can simplify a little bit, cancel the 3 and the 9. So this is 3 pi h cubed over 100 between 0 and 10. Plug in 10, I get 3 pi times 10 cubed over 100. To finish up, I plug in 10 for h. I would get 3 pi times 10 cubed over 100. That's the same as, let's see, 10 cubed is 1,000, so 1,000 over 100 would be 10. So I get 3 pi times 10 minus what I get if I plug in h equals 0. So I have 3 pi times 10 minus 0, or 30 pi. And if we glance up at our original work, We see that 30 pi is exactly the volume we were supposed to get using the volume formula for a cone. And that completes the example. Our final example of using integrals to calculate some familiar volumes has to do with the volume of a hemisphere. Now we know how to find the volume of spheres. That's 4/3 pi r cubed. So the volume of a hemisphere would be 1/2 of that. In this particular case, the radius is 5, and that means we'll end up with 2/3 pi times 5 cubed, and I can rewrite that as 250 pi over 3. So we know the volume we should get after applying the Riemann integral method to finding the volume of the hemisphere. I'll start by labeling the dimensions of the hemisphere. There's only one to label, that's the radius, here given as 5. Now following our method, we need to slice the figure into pieces we know. And in this case, slices parallel we need to slice the figure into pieces we know. With disks as our slices again, we'll label the thickness of each disk as the delta HI, where H once again measures height from the bottom of the figure up to the disk, and the radius of the ith slice is r sub I. I know how to write down the volume of such a disk. It's pi times the radius squared times the thickness delta HI. As was the case in the cone, however, we need to rewrite the r sub I to be just in terms of h. Now in the cone, we were able to use similar triangles to accomplish that. Here we have to use the Pythagorean theorem. To highlight how that's going to work, I'll draw the segment that goes from the center of the hemisphere out to the edge of the slice. And now because we're dealing with a hemisphere, that has to be a radius of 5. Any segment going from the center of the hemisphere to the surface will have a length of 5. By the Pythagorean theorem, then, ri squared plus hi squared is equal to the hypotenuse 5 squared. Using the Pythagorean theorem applied to the triangle shown in red, I can rewrite r sub I in terms of h sub I. Now I could go further and actually solve for r, but notice in the volume of the disk, ri squared is actually what I want. So there's no need to do that work. And now I can write the volume of the disk is pi times ri squared, which is the same as 25 minus hi squared delta hi. With that as the volume of one of my familiar pieces, the volume of the hemisphere would roughly be the sum of all of those individual pieces. Thus, the volume of the hemisphere would be exactly equal to the limit as I take the number of disks and let it go to infinity. We recognize that what we've done is construct a Riemann integral for the volume of the hemisphere, where I'm integrating the function from inside the summation, that's pi times 25 minus h squared, and the delta hi, as it gets thinner and thinner with the number of disks going to infinity, that becomes my dh. I need to determine the limits of integration. The smallest hi could be would be if the slice was sitting on the bottom of the hemisphere. That would be a value for h of 0. And then the biggest h could be is if the slice was at the very top of the hemisphere, and that would represent an h of 5. To finish up, the fundamental theorem allows us to evaluate this integral by finding an antiderivative instead of doing all of the limits. First, I pull a pi out in front of the integral. And that allows me to see the antiderivative for 25 minus h squared as 25h minus h cubed over 3, all evaluated between 0 and 5. If I plug 5 in for h, I get 125 minus 125 over 3, all times pi, and then if I plugged in h equals 0, I would subtract 0. (125) minus 1/3 times 125 is 2/3 times 125, and that can be rewritten as 250 pi over 3, and that's exactly the value we got when applying the formula for the volume of a sphere. So once again, our Riemann integral method, while admittedly more complicated than just applying the formula, has yielded a correct answer. This will give us some confidence when we move into less familiar examples that the method is sound. So when we go to calculate volumes that we can't check in any other way, we'll know that we're doing it right.